Well, it's a pleasure to be here. I remarked to Max that we have two titles of our talks which are as similar as they can possibly be without our talks being on the same thing at all. So it'll be quite interesting. So entropy is non-decreasing in a closed system. This is a strong statement that's been with us for a long time. And as Max said, this is one of the, holds the supreme position among the laws of nature. I won't do Max's British-Swedish accent imitating Eddington. And this is still true today. You know, if you propose a theory in which the entropy decreases, I think this is still a major problem, other than entropy fluctuations and so on that we can talk about. But this statement, entropy is non-decreasing in a closed system, almost every aspect of it is kind of confusing and under contention. What is a closed system? What is entropy? What sort of entropy generically increases in a closed system? And the picture that we have in mind, I think, when we talk about entropy increasing in a closed system is one like this. You have a box of gas. Maybe at some point, maybe initially, you've got some extra gas in a corner of the box. And time naturally leads the gas to diffuse out into the rest of the box. Or you put some creamer in a coffee, and naturally the coffee becomes uniform rather than the cream just sitting in one place, and the coffee never spontaneously moves into cream in the corner that plops out of the glass. Occasionally that could happen, but exponentially rarely. So the second law is a statistical one, but it's one that holds with enormous regularity due to the enormous number of particles involved. Now, the second law is talked about in a closed system because, of course, we can lower entropy by sticking something in a refrigerator. We can always lower entropy at the expense of raising entropy somewhere else by more. But the idea is that if you circumscribe some system and cut it off from outside contact, that the entropy should increase. Now, there are kind of closed systems like this room that's closed for some purposes, a large patch of space where you can approximate the linkages with the outside world as being small. But you can also imagine like really quite closed systems, like super isolated qubits in a lab that have been carefully isolated from the environment so things like decoherence don't happen. You can talk about a space-time region that is collapsing at the speed of light, so no outside influence can actually affect it. That's the domain of dependence of some region. So that's a closed system in principle, at least up to possible gravitational effects, because just it can't depend on the outside world. Or the universe, the ultimate closed system. So if you have a closed universe, or maybe even an infinite open one, if you take the whole thing at some time, that's a closed system. And I'm going to focus, for the purposes of this talk, on genuinely closed systems, by which I mean there's a fixed state space for the system and unitary evolution. And I'm interested in that because I think, while I agree with almost everything in Max's talk, the sort of description of the second law that he gave in terms of sort of information being lost because of correlations with the environment is not the same sort of explanation that we think of for say, why your house is messy. You know, your house gets messy if you've got two kids like I do, because those kids have their own dynamics, and those dynamics have no care or regard whatsoever for the sort of states you think about as clean or less less clean. So they go through their dynamics, and they just tend to move into states of less and less cleanliness, higher and higher mess, which has nothing to do with the fact that things are coming in or out of the house. It's just a mismatch between their dynamics and the states that you've defined as being of your interest. And so to think about how that sort of entropy increases, or how we can describe it, let's think about sort of definitions of entropy. So classically, imagine we have some state space represented by that shaded region. And it's got some microstates that it's made up out of that might have probabilities p sub I, or some probability density rho if it's continuous. Now, oh, some of the symbols didn't come out. We can partition this up into macrostates. I'll use A's for macrostates. And we could assign those probabilities given by the amount of sort of total probability of the microstates within those macrostates. So just sum up the probabilities within one of those macrostates. And we could also, if we'd like, count up the number of states in some macrostate, or the volume and phase space of some macrostate. So now there are a few different kinds of entropy we talk about in classical physics. One is the thermodynamic entropy, which you might define like within the formal system of thermodynamics as dq dt over dt, or log of the space of the state density in energy. And we'll come back to that a little bit. Most commonly, you talk about the Gibbs entropy, which is taking those probabilities of microstates, basically the Shannon entropy of those probabilities. And that, as Max noted, is preserved under Hamiltonian or Liouville evolution. So that is a kind of entropy that quantifies how much, sort of what is the information that is embedded in that probability distribution about the states. And that information is preserved by Hamiltonian evolution and doesn't go away. There's also, though, a notion of Boltzmann entropy, which is you consider a macrostate, or you consider a microstate and ask what macrostate that's in, and then you assign to that macrostate an entropy which is given by the log of the number of microstates in it. So this assigns an entropy to each microstate and to each macrostate. And this entropy tends to rise for sort of random microevolution with negative fluctuations in entropy exponentially suppressed. And the reason is sort of the obvious one that, let me get a pointer, that if you start out somewhere, say in this tiny corner of phase space where all the gas is collected in the corner of a room, whereas some of these big macrostates out here are things like gas is spread out all over, or gas is pretty spread out but kind of condensed in one corner, then if you just wander around and if your microevolution doesn't know about this drawing of macrostates that you've made, then it's just going to tend to wander into ones of higher and higher entropy because they have more and more volume of phase space. And if it doesn't know, it can't avoid going into higher and higher volume ones. So if you have a microstate, say, that starts out down here with small Boltzmann entropy, it will tend to wander into macrostates with higher and higher Boltzmann entropy. If you think about the Gibbs entropy, it will start out, say, in this little box. It'll get spread around through the unitary dynamics, but in fact, the volume and phase space of this will be the same as that, so the Gibbs entropy ends up being preserved. Now, oops, wrong pointer. Now, in quantum mechanics, we can actually do something quite similar. Rather than phase space, we have a Hilbert space, and we can define a density matrix on that Hilbert space, or individual states if we like. We can also partition Hilbert space into macrostates. And the way we can do that is to set up a set of projection operators that sort of sum to be the unity projector operator. So they and are orthogonal. So they partition the Hilbert space up into different Hilbert subspaces that are projected to by those projection operators. Then we can say the probability of being in some macro state, a big piece of I, is the trace of that projector operating on the density matrix. And we have a von Neumann entropy of the density matrix given by minus trace rho log rho, which is very closely analogous to the Gibbs entropy. You can think of, if you write the density matrix, if you diagonalize the density matrix, then it's the probabilities of those diagonal entries are probabilities. The Shannon entropy of those is the von Neumann entropy. So we've got that quantum entropy. But like Gibbs entropy, this von Neumann entropy does not change. So if we're looking for a chain or the second law for a closed system in quantum mechanics, this does not give it. It doesn't change. It just sits there. It doesn't decrease, but it doesn't increase either. Now, the common view, I would say, which is the one that Max discussed, is that we say, well, yeah, it's not really a closed system. We couple it to the environment, even if it's a weak coupling. And the dynamical degrees of freedom inside the system get entangled with those in the environment. And when we stay limited to the system of interest, that means we have to marginalize or trace over the environment. And that von Neumann entropy will go up. And this sort of reflects a sort of lack of, or a decay of the microscopic understanding that we had of that system because it's tied up with an environment which we're now ignoring. So that's one common view, but that is not really a view of a closed system, right? We're letting the system be open and the information is going because it's leaving the system. Another common-ish view, which sometimes goes under the name of eigenstate thermalization and things like that, is to say, we'll keep the system genuinely closed, but we'll just arbitrarily divide it into, say, 2, trace over half of it, and then look at the entropy of the other half. So this is a sort of measure of how the system is entangled with itself. This has interesting properties that are fairly independent of the partition, but it's a little bit artificial, because why that part, why did you consider these 2 independent states? Why this tracing over that half, and so on? So it's an interesting measure, but it's not really getting at that same question of that the Boltzmann view addresses, which is why sort of disorder is increasing. Why do we lose our description in the variables of our interest of how the system is behaving? The Boltzmann view is that there's this genericness or disorder that increases due to this inevitable mismatch between the dynamics of the system that we're talking about. It's sort of underlying microscopic dynamics and our definition of macrostates. So I was kind of surprised. This question's been bothering me for a long time, and I just sort of assumed throughout the years that there was an equivalent of classical Boltzmann entropy in quantum mechanics. So I went looking and trying to understand how that worked, and I kept not finding the equivalent of Boltzmann entropy in quantum mechanics. And so we had a postdoc, and I said, go find the equivalent of Boltzmann entropy in quantum mechanics. And he kept coming back and saying it's not there. So it seems to not be there. So we invented the equivalent of Boltzmann entropy in quantum mechanics. And the way that it works, the definition that we came up with, works like this. This is paper with Dominik Safranek, that's a postdoc, Josh Deutsch, and I. And you can find it in this short version, and there's a long version appearing soon. So we can think of, as we did for Boltzmann entropy, the volume of a macrostate. That's now given by the dimension of the Hilbert subspace that is that macrostate. And then we can say, suppose that macrostate has a probability p sub j. We can assign to a microstate, we can imagine that there's a probability that we're in some macrostate, but once we're in that macrostate, then following Boltzmann, let's attribute equal probability to each of the microstates in it. And that's sort of what Boltzmann entropy does. So we're going to assign micro-probabilities to each microstate I in a macrostate J as just the probability of that macrostate divided by the number of microstates, or the volume of that macrostate trace of p sub j. Okay, so that gives us a probability for each microstate where we've made this assumption that given that we're in some macrostate, we don't know what microstate we're in within that. Then take the Shannon entropy of those micro probabilities, and you get this expression. So it's a sum over the big p sub j's log p sub j over that Hilbert space volume. You can also interestingly write it in this way, in these two terms, which I'll come back and interpret later. Okay, so it's a fairly simple expression that will get somewhat more complicated later as we do more things with it. But it can be written in terms of these two terms, which I'll talk about later. Now, the crucial thing about this is that it both takes this kind of philosophy that once we sort of know what macrostate in, we're going to attribute equal probability to the microstates. And it's set up so that if we pick a state or a density matrix that's wholly enclosed in one of the macrostates, then this entropy, which we're going to call the observational entropy for reasons that will become clear, is just the volume of that macrostate, the Hilbert space volume of that macrostate, just like in Boltzmann entropy, right? So if we say we're a microstate in some macrostate, we assign to it the log of the volume of that macrostate. Same thing here, if the density matrix or state is wholly enclosed within a macrostate. Okay, so let me give a little motivation or sort of interpretation of beyond what I've just said for why we're thinking about this way. So first, unless you sort of prepare a system yourself or are like handed a little notebook that says what the density matrix for that system is, you don't know its density matrix, right? Any more than you know its quantum state. You can figure it out potentially if you were given infinitely many copies and a measuring apparatus. So you could figure out the probabilities, you could figure out the density matrix if you could choose a basis you want, or the state, and so on. So the way we do physics in the real world is not to know the density matrix of things, but to make a bunch of measurements about them, try to determine some results, and then try to make predictions about future measurements. So we might try to estimate the density matrix by making a bunch of measurements, but we're generally not given the density matrix. And so part of the philosophy of this observational entropy is that it's tied to probabilities for these measurements. So you define a set of observables, a set of measurements that some observer might make, and they can be coarse-grained measurements, not necessarily individual states, but coarse-grained measurements like the energy is in some range, say. And we really talk about the probabilities of those measurements and construct the idea of entropy out of those. And so the idea is that if we don't know what rho is and we measure that we're in some macro state, then we think of the post-measurement density matrix as being the density, sort of the maximum entropy density matrix that subject to it being in that macro state. So we kind of think of it as being in the density, the most ignorant density matrix compatible with what we have just measured. So that's another way to look at this. We can think about what the observational entropy does as measuring, if we have some set of measurements in mind, that it will measure the mean information gained in that set of measurements, plus the mean information left over after the replacement. So this is sort of an entropy, which is the mean, and entropies are always sort of mean information gained if you're doing a measurement in this form. So this is the mean information gained at the macro level by doing those measurements. This is a weighted sum, a probability weighted sum of the sort of uncertainty left, that is the amount of volume of the Hilbert space left after the measurements were made. So that's one way to think of it. Another information theoretic way to think about it is that if you think of some set of measurements that you're going to make, there's a, how much time do I have left? Sorry.
8 minutes to your 5 minutes.
8 minutes to my 5 minutes, okay. That it's the difference, the information theoretic difference, the Cooler-Leblanc divergence between the probabilities of those measurements on the density matrix that you have versus the maximally uncertain density matrix. So it's kind of how far away you are from maximum uncertainty as discussed by the observations that you're planning to make. Another way to look at it is that the density matrix contains sort of all the information that an observer could, in principle, extract from the system. If it didn't know anything, in principle, it could extract all that information. Doing so, it would have to do a very careful set of just the right measurements. The information that it could, in principle, extract is the difference between the von Neumann and the maximum entropy. That is the sort of log of the dimension of the full Hilbert space. And that information that is extractable from the density matrix is preserved by unitary evolution. But observers don't usually or can't ask precisely these questions. So given a set of questions they can ask, then this quantity, the difference between the maximum and the observational entropy, kind of measures the information that is extractable given the observations that they actually can make. And if you make just the right coarse-grained measurements, that equals the other one. So this will equal the von Neumann entropy if you pick just the right basis and make just the right fine-grained measurements. But unlike the von Neumann entropy, the observational entropy can increase as a mismatch develops between the questions that you're asking and the microdynamics that the system develops under. So this entropy has interesting properties. It's bounded in the sense that you might think. It's lower bounded by the von Neumann entropy, upper bounded by the maximum entropy. It's aclassical in the sense that a single microstate, even a pure state, can spread across many macrostates. So even a pure state can have maximal entropy, and this is a big difference from the von Neumann entropy. It's extensive. If you have a separable system, then the entropy of this whole system will be the sum of the entropies of the subsystems. It's constant under evolution if the coarse graining that you're measuring things in commutes with Hamiltonian. And this makes sense because in that case, you're tracking degrees of freedom that are preserved, that are conserved by the Hamiltonian evolution. so this entropy stays constant, but otherwise it tends to increase. And to see that, if you consider a coarse graining that doesn't commute with the Hamiltonian, and imagine starting in some macro state, that is the sort of density matrix is wholly contained within that macro state, then the initial observational entropy is log of the dimension of that macro state. You can show analytically that initially the observational entropy increases or is constant, so instantaneously it has to increase. And then numerically, we can show that under that Hamiltonian evolution, it increases approaching some equilibrium value. So we've done a whole bunch of numerical simulations. Very quickly, this is 4 particles and 16 cells. Quantum simulations are super expensive and hard, right? Partitioned into 4 macro states, so these are the 16 cells, the 4 particles, 4 macro states. Starting out with all 4 particles in the left half of the box, and then letting it evolve, and you see the entropy starts here, corresponding to in the left half of the box, increases rapidly up to near some maximum, and then just fluctuates up and down. So again, it quantifies an observer's loss of understanding of a system through its time evolution. And this is sort of potential understanding, right? So this is not letting the observer actually do the measurements. That would change the entropy in a way that Max described earlier. So this is a loss of sort of the ability to understand the system if you were to do the measurements. However, this equilibrium entropy, the one on the last slide, doesn't necessarily have to be the thermodynamic entropy. The thermodynamic entropy is closely tied to the energy, and so we have to do a little more work to get something that is comparable to the thermodynamic entropy in particular. This requires talking about multiple coarse grainings. So you can do, so this really corresponds, I've been saying a sequence of measurements, but really what I talked about before was sort of one measurement of one thing. To do a sequence of measurements, you'd need different coarse grainings, one for each type of measurement that you're doing. My pointer seems to have died, but that's all right. If those measurement operators, those projection operators commute, then it turns into a single coarse graining. If not, then the sequence of coarse grainings doesn't actually make a coarse graining, because non-commuting projectors don't make a new projector. But we can still define things in a way that maintains the previous properties, but depends on the ordering of the coarse grainings. And what's really interesting is that there are a lot of beautiful mathematical properties that we've been able to prove, including the entropy bounds, that it's between the von Neumann and the maximum entropy, even for that. Thank you. Even for multiple coarse grainings. Good. Now, there are 2 versions that can approach the thermodynamic entropy, and I'll have to do them, unfortunately, a little quickly. One is if you measure the coarse grain or measure in position and then energy. So you'll get an entropy that has an expression that looks like this. These are probabilities of being in that position bin and that energy bin, and these are volumes of those bins. And the interpretation is that an observer considers approximately measuring position, then precisely measuring energy. The position measurement then spreads out the system in energy, but not by much if it's already well localized, but by a lot if it's very spread out. And so this will tend to be a low entropy if the system is very localized in position, and high if it's not. Another way of doing something comparable is to decompose the system into different parts that have some coupling between them, and then coarse grain and projectors in those local Hamiltonians. We call this the factorized observational entropy. The interpretation being that an observer considers approximately measuring by projecting onto these spatially localized energy states. If the system's energy is relatively localized, then this is low, otherwise it's high. Now, analytically, we've been able to prove some nice things about these. The SXZ, which we generally call sexy, and FOE, which we call faux. They're actually more or less the same thing, so you can just imagine a sexy faux for convenience. And most of the things that we have been able to prove have been about the FOE. It turns out that we can show that the FOE for a microcanonical state, that is a bunch of microstates near the same energy, converges to the microcanonical entropy. It's upper bounded by the canonical entropy. For a thermal density matrix, it's close to the canonical entropy. It converges weakly to the canonical entropy for weakly open systems. All of this is kind of a bunch of results that basically show that either of these entropies turns into the thermodynamic entropy, both away from and certainly in the thermodynamic limit. Again, to show some numerical results, this is the same set of simulations. Now, starting out with everything confined to the first 8 cells, and then at time t equals 30, coupling to the other cells. And you can see that the system just sits kind of in equilibrium. Once it's coupled, it goes up, okay, to this higher equilibrium. And so we have here a way in which we can describe both equilibrium and non-equilibrium entropy. And this is an estimate of the thermal entropy. Now, because this is 4 particles in 16 slots, we're not going to get things exactly right. But there's good reason to think that in the thermodynamic limit, we will get the actual entropy to high precision. This is another plot that shows the entropy is a function of different sorts of states. So these are individual eigenstates. So again, it's not 0. This is not the von Neumann entropy. It's high. This is the density of states entropy. This is microcanonical initial condition, and so on. So these are all sort of have the same pattern. We can actually, through some heroic efforts of Josh, estimate these order 1 corrections. And if you make those, then in a plot that I would not believe if it came from a grad student, they all just line up beautifully, in fact. And all of these differences are expected to disappear in the thermodynamic limit. So, in conclusion, I would say a useful view of the second law, I think, and I almost think that there should be a different word for this kind of entropy than the von Neumann or the sort of entropy that Max was talking about, because they're really talking about different things, except that they both equal the thermodynamic entropy, and so you use the same word for them. But a useful view of the second law, I think, is this mismatch between a coarse graining and its variables, the variables that we use as observers and macroscopic beings, and its actual underlying dynamics. Boltzmann entropy encapsulates as well, generically rising even under information-preserving evolution in a closed system. This quantum Boltzmann entropy we call observational entropy can be defined, that does the same thing, and it has many nice entropy-like properties, connects with other entropies, provides a plausible story and quantitative measure for how disorder spontaneously arises in quantum systems that are truly closed, and applies dynamically and arbitrarily far from equilibrium. So this could be so I'm quite excited about this actually because it's got anywhere that you see entropy and you're out of equilibrium, this is a notion that can usefully and quantitatively apply that is all rigorously and well defined. So I'm excited to see what we can do with it. Thanks.